Somewhere beneath your feet, right now, heat is moving. Not the heat of a stove or a summer afternoon, but something slower and older. A warmth that has been traveling upward through solid rock for longer than any human lifetime, patient in a way nothing on the surface of the world ever needs to be. You cannot feel it, you cannot hear it. It simply continues, the way your own breath continues while you sleep, unattended and automatic, and yet entirely necessary. Tonight, we are going to follow that warmth for a while, not urgently, not with alarm, just gently, the way you might follow a single candle flame with your eyes until your eyelids grow heavy. Let's begin by imagining a place. Picture yourself standing at a safe distance, out on an open plain, maybe scrubby grass underfoot, the air cool and a little metallic, the way it sometimes smells before rain. In the middle distance there is a mountain. It is not doing anything dramatic. There is no fire, no explosion, no drama at all. It simply sits there, dark and broad-shouldered against the sky, its upper slopes catching the last blue light of evening. A thin wisp of something pale drifts from somewhere near its peak, so faint you might mistake it for a passing cloud that happened to snag on the summit. You could stand here for hours, and nothing more would seem to happen. And that is, in a strange way, the truest picture of what a volcano usually is. Not a catastrophe. A presence. A slow, breathing shape on the horizon that is doing something ancient and enormous, so gradually that from where you stand, it looks like stillness. We are conditioned, most of us, to think of volcanoes as sudden things. Explosions, rivers of orange light, screaming headlines and evacuation orders, and it is true that volcanoes can do all of that, and we will talk about those moments later, carefully, and without hurry. But if you spend any real time with the science of these mountains, the first thing you learn is that eruption is the exception, not the rule. A volcano might spend centuries in near silence, for every single day it spends erupting. Most of its life, like most of any life, is spent simply existing, holding its shape, slowly rearranging the rock beneath it, waiting, if a mountain can be said to wait at all. So tonight, instead of starting with fire, let's start with something quieter and, I think, more interesting. The idea that a volcano is not really a thing that happens to the Earth. It is a window into what the Earth already is. Here is what I mean. When you look at the ground beneath you, at a sidewalk or a garden bed or the floor of your own room, it is easy to imagine that the planet is essentially solid all the way down, one great continuous mass of rock, cool and settled, like a stone that finished cooling billions of years ago and simply stays that way now. This is a very reasonable thing to imagine because it matches everything we experience directly. Rock feels hard, mountains feel permanent. The ground does not move under our feet most days, in most places. Our senses, built for a human lifespan and a human scale, tell us that the Earth is finished, static, done. But the Earth is not finished. It is still, in a very real sense, cooling. Not on any schedule you or I would notice, but the planet formed around 4.5 billion years ago out of colliding debris, out of the crushing and clumping together of smaller rocky bodies, and that violent birth left behind an enormous amount of heat. Some of that original heat is still there, banked deep inside the planet like coals at the bottom of a fire pit hours after the flames have gone out. And more heat is being generated even now, quietly, by the slow radioactive decay of certain elements buried in the rock, elements like uranium and thorium and potassium, breaking down atom by atom, releasing tiny amounts of energy that add up, over the vastness of the Earth and the vastness of time, to something significant. So, the planet beneath you is not a cold stone. It is something closer to a very slowly dying ember. vast beyond imagining, wrapped in a thin, cool crust. That crust, the part we live on, the part that grows our food and holds our cities, is remarkably thin compared to the whole. If you imagine the earth as roughly the size of an apple, the crust we stand on would be thinner than the apple's skin. Beneath that skin lies the mantle, a deep layer of hot rock that behaves, over long stretches of time, almost like a very thick, very slow-moving fluid, not liquid in the way water is liquid. If you touched it, if such a thing were possible, it would feel completely solid, hard as any rock you've ever picked up. But given enough time, thousands or millions of years, that solid rock can flow, the way a stick of very cold caramel might seem perfectly rigid in the moment, but will still, given a long enough wait, sag and bend under its own weight. A volcano, at its heart, is simply a place where the boundary between that hot, restless interior and our thin, cool skin becomes thinner than usual, or cracked, or otherwise open enough that material from below can make its way up and out. It is a seam in the world's fabric, a place where the deep heat of the planet's birth and the ongoing warmth of its slow radioactive burn finally finds a path to the surface, after traveling for who knows how many years through rock that seemed, everywhere else, entirely closed. I find something quietly moving in that idea, and maybe you will too, lying there in the dark. Most of what makes the Earth, is hidden from us. We walk around on the outer skin of an enormous, ancient, still warm body, and for the most part, we have no direct way of knowing what lies beneath, no window into the interior at all. We infer it. Scientists study the way earthquake waves bend and slow as they pass through different depths, the way certain rocks are flung up from below during eruptions carrying pieces of the deep earth with them, the way heat leaks out of the ground in measurable amounts, even in places with no volcanoes at all. Piece by piece, indirect clue by indirect clue, we have built a picture of an interior none of us will ever visit, and volcanoes are one of the very few places where that hidden interior actually reaches us, where the deep world briefly becomes visible, becomes touchable, becomes something you could, if it were safe enough, hold in your hand as a new dark stone, still faintly warm. So as you rest tonight, you might picture that mountain again, standing quietly on the horizon, patient, unhurried, its faint plume drifting sideways in some high, unseen wind. It is not a monster. It is not, most of the time, even especially dramatic. It is closer to a chimney, for a house so large that the house is the whole planet, a place where warmth generated deep in the structure of the earth finds its way, slowly, slowly, up and out into the open air. Everything else about volcanoes that we will explore together over the hours ahead, the different kinds of rock they are built from, the different ways they erupt or fail to erupt, the strange chemistry of the melted stone inside them, the reasons some volcanoes sit quietly for 1,000 years and others rarely rest at all, everything grows outward from this one simple, calming idea. The earth is still warm inside, and every so often, in certain places, that warmth finds a way to show itself. Let that thought settle for a moment, the way a stone settles slowly through still water. There is no need to hold on to anything more than this right now, just the mountain, quiet on the horizon, and the vast, dark, comfortable idea of a planet that has been gently cooling since before there was anyone here to notice, or to wonder, or to sleep. Let's take that idea of a warm planet and go a little deeper into it, the way you might sink a little deeper into a mattress once your body has stopped resisting sleep and started trusting it. Picture the ground beneath you right now, wherever you happen to be resting, under the floor, under the foundation, under the soil and the clay and whatever rock lies beneath that, there is a layer of solid stone that wraps around the entire planet like the shell of an egg. This is the crust, and it is the only part of the earth that any human being has ever directly touched. Every mountain ever climbed, every mine ever dug, every well ever drilled, all of it stays within this outer shell. And here is the detail that tends to surprise people the first time they hear it. The detail worth turning over slowly in your mind before it settles. The crust is thin. Not thin the way a blanket is thin, but thin compared to the size of the planet as a whole. If the Earth were shrunk down to the size of an apple, the crust would be roughly the thickness of the apple's skin. Everything you have ever stood on, every road, every forest floor, every seabed, exists within that skin. There are actually two different kinds of this skin, and they are not quite the same. Beneath the oceans, the crust is thinner, usually somewhere around 3 to 6 miles deep, and it is made of a dark, dense rock called basalt, the same kind of rock that often pours out of volcanoes as flowing lava. Beneath the continents, where you and nearly everyone you have ever known has spent their life, the crust is thicker, sometimes 20 miles deep, sometimes more, and it is made of a lighter, paler rock called granite, full of pale minerals that catch the light when you find them in a quarry or a mountainside. Geologists sometimes describe continental crust as floating on the denser rock beneath it, the way a block of wood floats a little higher in water than a thin plank does. It is not a perfect comparison, but it is a useful one to hold loosely in your mind as you drift. This idea of the continents as slabs of lighter stone, riding gently on something heavier underneath. And what is that something heavier? Beneath the crust, filling almost all the rest of the space between the surface and the center of the earth, is a layer called the mantle. It is by far the largest part of the planet, making up a little more than 80% of the Earth's total volume. So large and so thick that if the crust is the skin of the apple, the mantle is almost the entire fruit inside it, everything but a small core at the very center. The mantle extends downward for roughly 1,800 miles, which is difficult to picture in any ordinary way, but you might try this. Imagine driving at highway speed, without stopping, for well over a full day, and you still would not have covered the distance from the top of the mantle to its bottom. That is how much rock lies beneath the ground you are picturing right now. Here is where the story tends to surprise people for a second time, and it is worth sitting with this one a little longer, because it is easy to misunderstand. The mantle is not, for the most part, liquid. This surprises many people who grew up imagining a great underground ocean of molten rock just beneath their feet, something you might fall into if the ground gave way. That picture, appealing as it is for daydreams and old cartoons, is not quite accurate. Almost all of the mantle is solid rock. It is under such enormous pressure and at such enormous temperature that it behaves in ways solid rock at the surface never would. But if you could somehow cut out a piece of it and hold it in your hand, cooled and depressurized, it would simply be a heavy, dark stone, not unlike some of the rocks you might find at the base of a volcano, since in fact that is sometimes exactly where such stones come from, carried up from the mantle by rising magma and dropped at the surface for patient scientists to study. So if it is solid, how does it move? How does it carry heat upward at all? Slowly enough to build mountains and continents over millions of years, but persistently enough to keep the whole system turning over across unimaginable stretches of time. The answer has to do with something called plasticity, a word that in this context does not mean the rock is like the plastic in a bottle or a toy, but rather that it can flow very, very slowly, without ever melting or breaking. Think of a thick bar of modeling clay left on a shelf. Over the course of a single afternoon, it looks solid, unchanging, entirely still, but leave it resting at a slight angle for a year, and you might come back to find it has slumped, sagged, taken on a new shape, all without ever becoming liquid at any point along the way. The mantle behaves something like that, but on a scale of millions of years rather than months, moving at a pace so slow it is often measured in inches per year, roughly the speed at which a fingernail grows. And yet, given enough time, and the Earth has had an extraordinary amount of time, that slow creeping motion is enough to carry heat from deep within the planet all the way up toward the crust above. Why is it hot down there in the first place? This is one of those questions that seems like it should have a single simple answer, and instead has several, layered on top of one another like blankets on a cold night. Part of the heat is left over from the very beginning, from the violent, chaotic process by which the Earth itself formed, roughly 4.5 billion years ago, when countless smaller bodies of rock and metal collided and merged together under the pull of gravity, each collision releasing a burst of energy, until enough of that energy had accumulated to melt the young planet almost entirely. Some of that ancient warmth, remarkably, has never fully escaped. It has simply been leaking outward, slowly, for billions of years, the way a stone pulled from a bonfire the night before might still hold a trace of warmth in its center the following afternoon, even after its surface has gone cool to the touch. But there is another source of heat as well, one that is quieter and steadier and, in its own way, even stranger. Scattered through the rock of the Earth's interior are tiny amounts of certain elements, uranium, thorium, potassium, that are radioactive, meaning their atoms are slowly, patiently breaking apart over time, and each time one does, it releases a small amount of energy as heat. Any single one of these tiny events is far too small to notice, but across the entire volume of the planet, over billions of years, those small events add up to a genuine and ongoing source of warmth, one that continues even today, quietly, invisibly, in the rock beneath every place you have ever stood. In a sense, the Earth is warmed both by memory and by patience, by the leftover heat of its violent birth, and by the slow, steady decay of atoms, too small to ever be seen. All of that heat has to go somewhere. Heat, as a rule, moves from warmer places to cooler ones, seeking always to even itself out, the way a warm room slowly cools once you open a window into the winter air outside. And so the heat of the mantle drifts upward, toward the crust, toward the surface, toward the cool, open sky above. Most of the time, this happens so gradually, so evenly, spread out across the entire globe, that you would never notice it happening at all. But in certain places, for reasons that have to do with the way the crust is broken and shifting above the mantle below, that heat does not spread evenly. It gathers, it concentrates, and it begins, slowly, to melt the rock around it into something new. Rock, it turns out, does not melt the way ice melts, all at once, at one clean, particular temperature. Ice is a single substance, water molecules locked in a simple crystal, and so ice has one melting point, the same everywhere, always, reliably 32 degrees Fahrenheit at sea level. Rock is nothing like that. Rock is a mixture, a rough congregation of many different minerals pressed together, each one a slightly different recipe of atoms, and each one, therefore, with its own particular temperature, at which it begins to soften and give way. Some of those minerals will start to melt at temperatures that would seem almost modest by the standards of the deep earth. Others hold their shape stubbornly, refusing to soften until the heat around them becomes far more extreme. And so when a body of rock gets hot enough to begin melting at all, it does not transform all at once, the way a block of ice slips into water. It melts a little at a time, one mineral surrendering before another, the most easily melted portions turning liquid first, while the rest remains stubbornly solid around them, like a fruitcake left too long near a warm oven, where the soft parts begin to sag and glisten, while the harder pieces still hold their shape. Geologists have a name for this gradual, partial softening. They call it partial melting, and it is worth sitting with that phrase for a moment, because it explains something that might otherwise seem strange, which is that the rock, deep inside the earth, is not simply either solid or liquid, the way we tend to imagine it, but is very often something in between, a mush, a slush, a mixture of the two existing together in the same place at the same time. This alone would be a reasonably useful piece of understanding, but it does not yet explain why the rock melts at all, in this place rather than that one, at this moment rather than some other. And here we arrive at something that tends to surprise people the first time they hear it clearly explained, because it runs against the instinct most of us carry, which is that rock melts simply because it gets hot enough. Heat matters, of course, but it is not the whole story, and in many of the most important cases, it is not even the main character. The other, quieter factor is pressure. Consider, for a moment, that the deeper you travel into the earth, the greater the weight of rock pressing down from above. Miles upon miles of solid stone, layered over more miles of stone, all of it bearing down under its own weight, the way the bottom pages of an enormous stack of books bear the weight of every page above them. That weight becomes pressure, and pressure, it turns out, has a peculiar relationship with melting. In general, squeezing a substance more tightly makes it harder for that substance to become a liquid, because melting requires the atoms or molecules within a material to loosen their arrangement, to spread apart from one another and move more freely, and it is difficult for them to do that spreading when they are being pressed together with tremendous force from every direction. So even in parts of the mantle where the temperature is genuinely hot enough, by ordinary standards, to melt the rock very often stays solid anyway, simply because the pressure holding it together is so immense. It is hot enough to melt, it is simply not allowed to. This is where something rather elegant happens, something that accounts for a great deal of how volcanoes come to exist in the first place. If a portion of that deep, hot, solid rock should happen to rise, even slowly, even by no more than the width of a hand each year, drifting upward toward the surface the way a very slow, very patient bubble might drift upward through honey, then the pressure surrounding that rock gradually eases. There is less stone above it now, less weight bearing down, and so the pressure relaxes, even while the temperature, remarkably, stays almost exactly the same. And at some point in that slow upward drift, the pressure may ease just enough that the rock is no longer being held back from doing what its temperature had wanted to do all along. It begins to melt, not because it grew hotter, but because it was finally permitted to. Geologists call this decompression melting, and it is worth pausing on how counterintuitive it is. The rock does not need a match set beneath it. It does not need some fresh burst of heat from somewhere else. It only needs room. It only needs, in a sense, to be allowed to relax. There is a second way that rock can be coaxed into melting, one that does not rely on pressure easing at all, but instead on a kind of chemical persuasion. You may already know, from ordinary winter experience, that salt lowers the melting point of ice, which is why salt is scattered across icy sidewalks and roads, encouraging the ice to soften and give way at temperatures where it would otherwise remain stubbornly frozen. Something rather similar happens deep within the earth, though the substance doing the persuading is not salt but water. In certain places, water finds its way down into very hot rock, carried there by the slow, grinding motion of the earth's outer shell, and when that water mingles with the hot mineral grains around it, It interferes with the tidy crystal arrangements holding those minerals together, loosening their bonds the way salt loosens the bonds within ice. The rock, as a result, begins to melt at a temperature considerably lower than it would have required on its own, without any need for additional heat and without any need for reduced pressure. It melts simply because water has been introduced into a place where water does not usually belong, and the rock, so to speak, cannot hold its shape quite so well with that intruder mixed in among it. So there are, in fact, at least two quiet and rather different paths by which solid rock can become the flowing, glowing liquid we call magma, one having to do with the easing of pressure as rock rises, and the other having to do with the softening influence of water seeping downward. Both are slow. Both are almost imperceptibly gradual, unfolding over years or centuries rather than moments. And once that melting has begun, once even a portion of once solid rock has become liquid, something else enters the picture, something that had been there all along but had gone unnoticed, held quietly in place. Gases. Magma is never simply melted stone and nothing more. Dissolved within it, invisible, are gases, mostly water vapor, along with smaller amounts of carbon dioxide and sulfur compounds, all of them held in solution, the way carbon dioxide is held in a bottle of soda, dissolved and quiet, and utterly undetectable, so long as the pressure around it remains high enough to keep it that way. Crack open that bottle, release the pressure even slightly, and the gas remembers itself all at once, foaming and rushing outward in a way that seemed impossible only a moment before. Magma, deep within the earth, carries its dissolved gases in much the same hidden, patient way, kept in solution by the tremendous pressure of all the rock and magma pressing around it. It is only later, when that magma begins its slow journey upward, when the pressure around it begins at last to fall away, that those gases will start to remember themselves as well, and begin, very quietly at first, to come out of hiding. Before we follow that magma any further on its journey upward, it might help to step back for a moment, to rest the mind on a wider view, and ask a question that seems almost too large to hold. Why does any of this happen where it happens? Why do volcanoes gather in certain places on the Earth's surface, tracing long curving lines across maps, while other places, just as old, just as rocky, remain quiet century after century? The answer, as it turns out, has less to do with any single mountain and more to do with the shape and behavior of the Earth's outer shell as a whole. And to understand that shell, it helps to imagine, very gently, something rather like an eggshell. Picture, if you will, a hard-boiled egg, its shell intact but laced all over with a fine web of cracks, the kind that appear when you tap it softly against the edge of a bowl. The shell has not shattered. It still holds its shape, still wraps around the egg in one continuous surface, but it is no longer a single, unbroken piece. It has become many pieces, fitted closely together, edges touching, and if you were to press on one piece, you might feel, faintly, some small answering shift in the piece beside it. The Earth's outer layer, the part called the crust, together with a thin, rigid portion of the layer just beneath it, is something like that cracked shell. Geologists call this whole rigid outer shell the lithosphere, and it is broken, has been broken for a very long time, into a number of enormous slabs. These slabs are called tectonic plates. There are perhaps a dozen or so major ones, along with a good many smaller ones tucked in between, and their edges do not follow any tidy pattern that a person might have designed on purpose. They cut across oceans and continents alike, indifferent to the coastlines we draw on our maps, indifferent to the borders between nations. One plate might carry beneath it the entire floor of an ocean along with the continent that sits at its edge, moving as one unified piece, while the boundary between it and its neighbor might run directly through what looks, from the surface, like perfectly continuous land. You would not necessarily know, standing at such a boundary, that you were standing at one at all. There is no seam visible to the eye, no stitching in the ground, and yet the plates are there, real and enormous, some of them larger than entire nations, some larger than continents themselves. Now here is the part that tends to surprise people the first time they hear it stated plainly, though scientists have understood it for the better part of a century. These plates move, not quickly, not in any way you would ever feel or notice in the course of an ordinary day, but they move nonetheless, drifting across the surface of the earth at a pace that is, frankly, almost comically slow by any human measure. A typical plate creeps along at something like 2 to 10 centimeters a year. That is roughly the rate at which a fingernail grows. If you were to stand at a plate boundary and watch very carefully for the whole of your lifetime, you would see, cumulatively, a gap open or close by perhaps the width of your outstretched arms. It is not a motion anyone has ever felt directly underfoot. It is a motion that can only be measured with patient instruments and confirmed, again and again, only across years of careful watching. And yet, slow as it is, this motion, sustained over millions of years, has reshaped the entire face of the planet more than once. The continents you know from any map today, the particular shapes of Africa and South America that seem to fit together almost like puzzle pieces along their coastlines, did not always sit where they now sit. There was a time, some 200 million years ago, when the continents were gathered into a single enormous landmass, one that scientists have come to call Pangaea, meaning, roughly, all the land. Pangaea broke apart slowly, its pieces drifting away from one another over tens of millions of years, and the oceans we sail today, the Atlantic among them, opened up gradually in the widening space between the drifting fragments. This was not obvious to anyone for a very long time. It was a scientist named Alfred Wegener, early in the 20th century, who first proposed in a serious and sustained way that the continents had once fit together and had since drifted apart, pointing to matching fossils and matching rock formations on opposite sides of the Atlantic as his evidence. He was, for decades, largely dismissed by many of his fellow scientists, in part because he could not offer a convincing explanation for what force might possibly push a continent across an ocean floor. It was only later, once evidence from the ocean floors themselves began to accumulate, that the fuller picture, the picture of moving plates rather than merely drifting continents, began to take clear shape, sometime around the middle of the 20th century. The question of what actually moves these plates is one that scientists have continued to refine even into recent decades, and it would be a small dishonesty to pretend the matter is settled down to every last detail. But the broad picture that has emerged involves the slow churning of the mantle beneath the plates, that thick layer of hot, softened rock we spoke of earlier, rock that behaves, over long stretches of time, almost like a very heavy, very slow fluid. Heat from deep within the earth causes portions of that mantle to rise, ever so gradually, while cooler portions sink, and this vast, patient circulation, along with the pull of old plate material, sinking back down into the depths at certain boundaries, drags and shoves the plates above it, inch by inch, year after year. It is something like the slow rolling of a pot of thick soup left on the lowest possible flame, where the surface seems still to a casual glance, and yet if you watched closely enough and waited long enough, you would see faint currents rising here and sinking there, carrying anything floating on top along with them. Wherever these great plates meet, at their edges, something has to give. And it is here, right at these boundaries, that most of the world's volcanoes are found. Sometimes, two plates are pulling apart from one another, drifting in opposite directions, and where they separate, hot mantle material rises up to fill the space between them, melting as the pressure eases in just the way we spoke of a little earlier, and new volcanic rock is added quietly along that widening seam. This is happening right now along the middle of the Atlantic Ocean floor, a process almost entirely hidden from view beneath thousands of feet of water, except in the one remarkable place where that seam happens to rise above the waves. Iceland sits directly astride this boundary, and it is, for that reason, one of the most volcanically active places on the surface of the Earth. A small island, quite literally being pulled apart and stitched back together at the same time, so slowly that its residents have built their whole lives, their farms and their roads and their small towns, across ground that is, in the most literal geological sense, still coming into being. Elsewhere, plates are not pulling apart but pressing together, colliding, and here the story unfolds rather differently, involving not gentle separation but a kind of deep, grinding encounter between one slab of the Earth's surface and another. And it is that encounter, that quiet and enormous collision happening in slow motion beneath our feet, that deserves its own careful telling. Before we follow the plates any further in their slow, grinding embrace, it might be worth simply pausing here, in this quiet moment, to picture the mountains themselves. All this talk of pressure and melting and rock rising through the dark can start to feel abstract, almost like a story about forces we cannot see, and in a way it is exactly that. But it produces something very real and very visible, something you could stand before and tilt your head back to look at, and it is worth taking the time now to imagine what these different mountains actually look like, because they do not all look the same at all. In fact, if you lined up pictures of the world's volcanoes side by side, you might be forgiven for not realizing they belong to the same family of landform. So different are their shapes, their slopes, their whole manner of standing upon the earth. Let's start with the gentlest of them, the shield volcanoes, so named because their outline, seen from a distance, resembles a warrior's shield laid flat upon the ground, curved and broad, and unhurried in its rise. These are not the sharp, dramatic peaks that most people picture when they hear the word volcano. They are wide and low, their slopes climbing so gradually that you could walk up one for an hour without feeling much steepness beneath your feet at all, and you might not even realize, standing partway up, that you were on the side of a volcano rather than simply a very large, very gentle hill. The reason for this shape lies in the kind of lava that built it. Shield volcanoes are made from lava that is thin and runny, hot and low in silica, the kind that pours out and spreads across the land the way warm honey spreads across a plate before it has had time to cool and thicken. It does not pile up steeply near the opening it came from. It flows and keeps flowing, sometimes for miles, before it finally slows enough to cool and harden, and so each eruption adds not a tall spike, but a thin, wide sheet, layered one atop another over many thousands of years, until the whole structure has grown into something enormous without ever once looking dramatic in cross-section. The islands of Hawaii offer the clearest example of this kind of mountain that we have anywhere on Earth. Mauna Loa, on the Big Island, is so vast that if you measured it not from sea level, but from its true base on the ocean floor far below, it would stand taller than Everest, and yet, because its slopes rise so gradually, so gently, a person standing at its foot might struggle to appreciate the scale of what loomed above them. There is something almost peaceful in this. The lava that built Mauna Loa and its neighbor Kilauea tends, most of the time, not to explode violently, but to well up and flow, sometimes advancing across a road or a field at a walking pace, slow enough that people have stood nearby and watched it come, slow enough that in past centuries, native Hawaiian communities developed whole traditions and stories around Pele, the deity understood to reside within these fires, a relationship to the volcano built not on constant terror, but on a kind of respectful familiarity, the sense of living alongside something powerful, but, most days, unhurried. Now picture something entirely different in size and temperament. The cinder cone, where shield volcanoes are broad and patient, built up so slowly you could scarcely see the growth happening. Cinder cones are small, steep, and can appear with startling speed, sometimes within a matter of weeks. They form when gas-rich lava sprays up into the air from a single vent, breaking apart as it flies, cooling in the air into small dark fragments called cinders or scoria, full of tiny holes left behind by escaping gas, light enough that you could hold a piece the size of your fist in one hand without feeling much weight in it at all. These fragments fall back down around the vent, piling up in a neat, steep-sided cone, usually no more than a few 100 feet high, with a bowl-like crater at the top where the fountaining lava sprayed skyward. One of the most remarkable and best documented examples of a cinder cone's birth happened in Mexico, in the state of Michoacán, in the year 1943. A farmer named Dionisio Pulido was working in his cornfield one February afternoon when he noticed a strange hissing sound coming from a small crack in the ground, a fissure that had not been there the day before. Smoke began to rise from it. By the next morning, a cone of ash and cinder had already grown taller than a house. Within a week, it stood well over 100 feet high, and the volcano, which came to be called Paricutin, after the nearby village, kept growing and erupting for 9 years before it finally went quiet, leaving behind a cone over 1,000 feet tall, standing where a cornfield had been. It remains one of the few times in recorded history that scientists were able to witness, from the very first hours, the entire birth and early life of a volcano, a strange kind of privilege granted to a farmer who had simply gone out that morning to tend his field. Then there is the third great shape, the one that probably comes to mind first for most people when they hear the word volcano at all, the tall, steep, almost perfectly symmetrical cone, rising to a point, its slopes far too steep to walk up casually, its silhouette so classically beautiful that painters and poets have returned to it again and again. These are called stratovolcanoes, or sometimes composite volcanoes, and their name comes from the way they are built, not from a single kind of material, as the shield volcanoes are, but from alternating layers, strata, of hardened lava, ash, and rocky debris, stacked one upon another over centuries, each eruption adding a new thin sheet to the mountain's flanks. The lava that builds these mountains tends to be thicker, stickier, higher in silica than the lava of a shield volcano, closer in consistency to cold honey or to toothpaste squeezed slowly from a tube, and because it does not flow easily, it tends to pile up close to the vent rather than spreading far and wide, building steep slopes rather than gentle ones. This same stickiness, as we will come to see, also has a great deal to do with why these particular volcanoes are so often the ones responsible for the most sudden and dangerous explosions, though that is a thread we can follow a little further on. Mount Fuji, rising alone above the plains of Japan, its snow-capped peak so often painted and photographed that it has become almost a symbol of the country itself, is a stratovolcano. So is Mount Vesuvius, looming over the Bay of Naples, quiet for so long now that in the year 79, the people of the nearby Roman town of Pompeii seem to have gone about their ordinary lives with little sense of danger, until the mountain erupted with terrible suddenness and buried the town beneath layers of ash so completely that it preserved, almost as if in a single frozen moment, the shapes of the daily life it had ended. And Mount St. Helens, in the state of Washington, whose eruption in 1980 was watched and recorded by modern instruments and cameras in a way no eruption before it had ever been, offering scientists an extraordinarily detailed record of exactly how a stratovolcano can hold pressure quietly for a long while and then release it all at once. So there they stand, these three broad families of mountain, each one a kind of portrait of the lava that made it. The wide, patient shield, built from lava thin enough to travel far. The small, quick cinder cone, built from fragments flung into the air and settled where they fell. And the tall, steep stratovolcano, built slowly from thick, reluctant lava that piles close to home, layer upon layer, and holds its breath, sometimes for centuries, before it finally lets go. And that question of holding the breath, of why some lava flows out calmly, while other lava seems to wait and gather itself before bursting free all at once, is really a question about a substance we have mentioned several times now, without yet looking at closely enough. It is time to think more carefully about the lava itself. Lava, it turns out, is not one single substance behaving in one single way, any more than honey and water are the same substance, simply because both can be poured. What determines whether a volcano oozes gently or explodes violently has almost everything to do with two things working together, quietly, deep beneath the surface, long before anyone on the ground notices anything unusual at all. The first is how thick or viscous the molten rock happens to be. The second is how much gas is dissolved within it, trapped there under pressure, waiting for its chance to escape. And it is the relationship between these two things, thickness and trapped gas, that decides whether an eruption will be the kind you could stand near and watch, almost like a slow river finding its way downhill, or the kind that gives no such comfortable distance at all. Think, for a moment, about opening a bottle of soda that has been sitting untouched in a warm room. If you loosen the cap slowly, carefully, the gas escapes in a thin, steady hiss, and the liquid inside barely stirs. But if that same bottle has been shaken first and then opened quickly, the gas does not leave calmly. It rushes out all at once, carrying the liquid with it in a sudden, foaming burst that can catch you off guard, even when you know, in principle, that it is coming. A volcano works on something like this same principle, though on a scale that turns a kitchen mishap into a landscape-altering event. The gas is there in the magma either way. What changes is how easily it can get out, and how much resistance it meets as it tries. In basaltic magma, the thin, runny kind that built the wide shield volcanoes we spoke of, the gas has a relatively easy time of it. The magma is fluid enough that bubbles can form and rise and burst at the surface in a fairly unhurried way, much like bubbles rising through a pot of water that is not yet at a full rolling boil. This is why eruptions from shield volcanoes so often take the form of what geologists call effusive eruptions, meaning the lava simply flows out, sometimes from a central crater, sometimes from long cracks called fissures that open along the volcano's flanks. There may be fountains of lava shooting upward, glowing orange against the night sky, spectacular to see from a safe distance, but the material itself moves at a walking pace, or even slower, giving people and animals time to move out of its path. Hawaii's Kilauea has produced eruptions like this many times, lava creeping across roads and fields over the course of hours and days, consuming what lies in its path with a kind of unhurried inevitability, but rarely catching anyone by surprise in the way a sudden explosion might. Now think instead about magma that is thick and sticky, the kind we have already met inside a stratovolcano, cooling and stiffening as it sits, so viscous that it resists flowing at all. Gas bubbles trying to rise through this kind of magma find themselves trapped, the way air struggles to escape from a very stiff bread dough, or the way a bubble caught in cold honey seems to hang there almost motionless, unable to find its way to the surface on its own. The gas does not simply disappear because it cannot escape easily. It accumulates instead, building pressure inside pockets and channels within the magma, sometimes for months, sometimes for years, sometimes, as at Mount St. Helens, for a period during which the mountain itself visibly swelled, its north flank bulging outward by more than 100 feet as magma pushed upward from below, straining against rock that had no easy way to relieve the pressure building within it. When that pressure finally exceeds what the surrounding rock can hold, the release is not gradual, it is sudden, and it is violent, in the specific physical sense of involving a great deal of energy transferred very quickly. This is what volcanologists mean by an explosive eruption, and it is worth sitting with the difference for a moment, because it is not simply a matter of degree, not simply a bigger version of the same gentle process. It is a different kind of event altogether, where an effusive eruption sends lava flowing outward at a pace a person could outwalk. An explosive eruption can send ash and pulverized rock and volcanic gas rocketing upward into the sky in a matter of seconds, forming what is sometimes called an eruption column, a churning tower of material that can rise many miles above the volcano's summit and be seen and feared from great distances. Sometimes this eruption column simply keeps rising, carried upward by its own heat, the way smoke rises from a chimney, eventually spreading outward at the top into a broad, flattened shape not unlike the top of certain tall clouds, before drifting downwind and settling as a fine gray ash over the surrounding countryside, sometimes for hundreds of miles. This ash, incidentally, is not soft the way ash from a campfire is soft. It is made of tiny, sharp fragments of glass and pulverized rock, and it can be heavy enough, when it accumulates on rooftops, to cause them to collapse, and abrasive enough to damage the engines of aircraft that fly through it unaware. But there is another possibility, one that is in some ways even more dangerous, and it happens when the eruption column loses its ability to keep rising, when it becomes too dense, too heavy with rock and ash, to be sustained by its own heat any longer. When that happens, instead of continuing upward, the column collapses back down upon itself, and the material within it, still scorching hot, still full of expanding gas, does not fall gently to the ground the way ash does. It rushes outward and downward along the volcano's slopes at speeds that can exceed 100 miles an hour, a churning, glowing avalanche of gas and ash and rock fragments known as a pyroclastic flow. There is very little time to outrun such a thing, and very little that can survive directly in its path. It was very likely something of this kind, a fast-moving surge of superheated gas and ash that overtook Pompeii and its neighboring town of Herculaneum in the year 79, arriving with a speed that gave the people caught in its path almost no warning at all. It is worth pausing here to notice that these two broad kinds of eruption, effusive and explosive, are not always cleanly separate from one another. A single volcano may show both behaviors across its lifetime, or even within a single eruptive episode, beginning perhaps with an explosive phase that clears out old, stiffened rock blocking its central vent, and settling afterward into a calmer, effusive phase as fresher, more fluid magma finds its way to the surface. Volcanoes, in other words, do not read the textbooks written about them. They tend, instead, to do whatever the particular combination of pressure and viscosity and gas content beneath them happens to dictate at that particular moment. And part of what makes the study of volcanoes so demanding and so genuinely uncertain even today is the difficulty of ever knowing, with real confidence, exactly what that combination looks like at any given depth, at any given time, hidden as it is beneath miles of solid rock. And yet, for all that uncertainty, there are patterns, gathered patiently over centuries of observation, that allow scientists to make reasonable estimates of what a particular volcano is likely to do, based on what it has done before, and based on the particular character of its magma. It is to those patterns, and to the long and often surprising history of how people first began to notice them, that we can turn our attention next. Before we look at those patterns of history, though, it helps to slow down and take inventory of what a volcano actually sends up into the world in the first place. We have been speaking of lava and ash and gas somewhat loosely, as though they were simple, single things, but each of them is really a small category of its own, with its own behaviors, its own textures, its own way of moving through the air or across the ground, and understanding those differences, gently, one at a time, makes everything that comes later easier to follow. Start with lava, since it is the most familiar, the substance most people picture when they hear the word volcano at all. Lava is simply magma that has reached the surface, molten rock that has escaped the pressure and heat of the Earth's interior and begun, for the first time, to be exposed to open air. But the word lava covers an enormous range of behavior, and much of that range comes down to a single property we touched on earlier: viscosity, which is really just a scientific way of describing how easily something flows. Thin, honey-like lava, low in silica and correspondingly low in gas, can travel remarkable distances. In Hawaii, geologists have documented lava flows creeping for many miles from a vent, sometimes taking days or weeks to reach the sea, moving at a walking pace, or slower, depending on the slope of the ground and how quickly the surface of the flow cools and thickens as it goes. This kind of lava often develops a strange, almost decorative texture as it travels. When its surface cools into a smooth, glassy, ropey skin, while the still molten rock beneath continues to push forward underneath, Hawaiian observers gave it a name that geologists still use worldwide: pahoehoe, a word that in its original context evokes the idea of something smooth enough to walk across barefoot, at least once it has cooled. Nearby, sometimes flowing from the very same vent only hours apart, a rougher, more broken kind of lava can form instead, its surface fractured into jagged, clinker-like chunks that shift and grind against each other as the flow advances. This is called a word that, according to a story told often enough to have become part of volcanic folklore, may echo the sound a person makes when trying to cross it with unprotected feet. Whether or not that origin is precisely accurate, the texture itself is real enough, and walking across a field of cooled today still means picking your way carefully over sharp, unstable rubble. Thicker, stickier lava behaves quite differently. Because it resists flowing, it tends to pile up close to the vent that produced it, sometimes squeezing out slowly enough that it barely seems to move at all, forming steep, bulging domes of rock that can grow for months or years, inching upward and outward the way a very slow-rising loaf of bread might push against the sides of its pan. These lava domes are, in their own quiet way, some of the more dangerous features a volcano can produce, not because they erupt violently themselves necessarily, but because their outer surfaces cool and harden even as the interior stays hot and mobile, and a dome can collapse suddenly, sending an avalanche of hot rock and gas down the slope with very little warning. Ash is a different matter altogether. and one of the more persistent points of confusion, because the word itself invites the wrong comparison. Volcanic ash is not soft and feathery like the ash left behind in a fireplace or a campfire. It is, instead, made of tiny, jagged fragments of pulverized rock and volcanic glass, shattered into pieces smaller than 2 millimeters across when magma is torn apart violently by expanding gas during an explosive eruption. Under a microscope, individual grains of volcanic ash often look like tiny shards of broken glass, because that is essentially what they are. And this is part of why volcanic ash is so much more troublesome than its name suggests. It does not simply drift down and settle harmlessly the way soot might. It can scour paint from cars, short out electrical equipment, contaminate water supplies, and, when inhaled, irritate lungs in a way that ordinary dust does not, because those sharp, glassy edges do not break down or soften the way organic ash would. A heavy enough ashfall can collapse roofs under its accumulated weight, since volcanic ash is considerably denser than snow of the same depth, closer in weight to wet sand than to anything most people would associate with the word ash at all. And ash can travel extraordinary distances once it is lofted high enough into the atmosphere. The eruption of Krakatoa in 1883 sent fine ash and aerosols circling the globe, producing vivid, unusually colored sunsets as far away as London and New York for months afterward, a phenomenon that puzzled ordinary observers at the time, many of whom had no idea that the strange, lingering red skies they were watching traced back to an eruption on the far side of the planet. And then there is gas, which is, in many ways, the least visible and yet perhaps the most consequential of everything a volcano releases. It is the gas, more than anything else, that determines whether an eruption will be gentle or explosive in the first place, since it is the sudden, violent expansion of dissolved gas escaping from magma that tears the surrounding rock apart and drives ash and pumice high into the sky. But volcanic gas has its own life beyond that initial explosive role. The gas that volcanoes release is mostly water vapor, which is generally the least troubling component, but it also typically includes substantial amounts of carbon dioxide and sulfur dioxide, along with smaller quantities of other gases that vary from one volcano to the next. Carbon dioxide is heavier than air, and because of this, it can pool silently in low-lying areas near a volcano, in valleys or depressions where the wind cannot easily disperse it, creating invisible pockets where the air is simply unable to sustain breathing. In 1986, at Lake Nyos in Cameroon, a sudden catastrophic release of carbon dioxide that had been quietly accumulating in the depths of a crater lake surged outward across the surrounding valleys in the middle of the night, and it claimed nearly 2,000 lives, many of them people who never woke to understand what was happening, since the gas itself was entirely colorless and odorless as it settled over their villages. Sulfur dioxide behaves rather differently. Rather than pooling near the ground, it tends to rise with the plume of an eruption, and once high in the atmosphere, it can react with water vapor to form tiny droplets of sulfuric acid, fine aerosols that can linger for months or even years, depending on how high they were injected and how large the eruption that produced them. These aerosols scatter and reflect a portion of incoming sunlight back toward space, and this is part of why very large eruptions have historically been followed by measurably cooler global temperatures for a year or more afterward, a connection that scientists did not fully appreciate until they began comparing careful records of past eruptions against equally careful records of past weather, piecing the relationship together gradually rather than recognizing it all at once. So when a volcano erupts, it is never really releasing one single thing. It is releasing lava that may crawl gently for miles or pile up into a slow, dangerous dome. Ash that behaves more like ground glass than like anything from a fireplace, and a mixture of gases, some of them capable of altering climate on the far side of the planet, others capable of settling, unseen, into a valley and taking lives without any explosion at all. Each of these behaves according to its own physical rules, and each has, at different points in history, taught the people studying volcanoes a lesson they did not expect to learn, often at considerable cost. It is worth turning now to how those lessons were actually gathered, to the long, patient, sometimes accidental process by which people first began to understand what they were looking at. Those lessons, it turns out, were gathered from a strikingly small number of places on Earth, because volcanic activity is not scattered evenly across the planet's surface. It clusters. If you were to mark every well-documented eruption of the last few centuries on a map, and then step back and look at the pattern from a distance, you would notice something that looks almost too tidy to be natural. A long, curving band tracing the edges of the Pacific Ocean, dipping down through the islands of Indonesia, up through the Philippines and Japan, across the Aleutian chain of Alaska, and down the western coast of the Americas, before curling back through the southern Pacific. People eventually gave this band a name that sounds almost cinematic, though it was coined simply because it describes what it looks like, the Ring of Fire. It is not an official geological term with sharp, agreed-upon boundaries, more a useful shorthand that emerged gradually as mapmakers and geologists compared notes, but it captures something real and worth sitting with quietly for a moment. The reason for the ring has to do with the structure of the Earth's outer shell, which is not one continuous surface but a mosaic of enormous rigid plates, drifting almost imperceptibly against one another, at speeds often compared to the rate a fingernail grows. Where two plates meet and one is denser than the other, the denser one is gradually pushed underneath, sliding down into the hotter depths of the mantle, in a process geologists call subduction. Picture a heavy wool rug being slowly forced under the edge of a lighter one on a wooden floor. That descending slab of ocean floor carries water down with it, locked into its minerals, and as it sinks and warms, that water is released and lowers the melting point of the rock above it, encouraging magma to form and eventually rise. Nearly the entire rim of the Pacific is lined with these subduction boundaries, one plate diving beneath another in a slow, continuous procession that has been happening for tens of millions of years. And that is why volcano after volcano appears along this same curving path, like beads threaded on a very long, very patient string. Japan sits almost squarely within this arrangement, perched at the junction of several plates that are all, in their own unhurried way, sliding beneath one another. This is part of why the country has such a long and carefully kept written history of both earthquakes and eruptions, stretching back over 1,000 years in some records, since a landscape that shakes and smokes with any regularity tends to produce people who write those events down. Mount Fuji, so often pictured as a serene, snow-capped cone, is itself a product of this same subduction process, though it has not erupted since the early 18th century, when ash reportedly fell as far away as the streets of what is now Tokyo, dusting rooftops many miles from the mountain itself. Indonesia occupies a similarly active position, sitting where several plates converge in a tangle that makes the region one of the most volcanically dense places on the planet, home to more than 100 volcanoes that have shown some sign of activity in recorded history. It was here, on the island then called Sumbawa, that Mount Tambora erupted in 1815 with a force so large it lowered global temperatures enough to disrupt harvests as far away as Europe and New England the following year, a season people at the time called, without knowing the actual cause, the year without a summer. And it was here, too, decades later, that the island of Krakatoa produced an eruption whose sound was reportedly heard nearly 3,000 miles away, a detail so extraordinary that for a long time it seemed almost unbelievable, until researchers cross-referenced it against reports from multiple, unconnected observers scattered across the Indian Ocean and beyond. Moving eastward across the Pacific, the pattern continues into the Aleutian Islands, a long arc curving off the coast of Alaska, formed by the Pacific Plate sliding beneath the North American Plate, and then down through the volcanoes of the American West, including the Cascade Range, home to Mount St. Helens, whose 1980 eruption remains one of the most closely studied in North American history, in part because scientists happened to be watching it so carefully in the weeks beforehand, tracking the way its north face bulged outward, day after day, like dough rising too fast, until it finally gave way. Continuing south, the ring runs down through Central America and along the western edge of South America, where the Andes hold one of the highest concentrations of volcanoes on Earth, a direct consequence of the Nazca Plate sliding beneath the South American Plate along nearly the entire length of the continent's Pacific coast. Not every famous volcano sits on this ring, though, and it is worth pausing on the exceptions, because they reveal a second, entirely different mechanism at work. Hawaii, for instance, sits nowhere near a plate boundary. It rests instead in the middle of the Pacific Plate, far from any edge, which puzzled geologists for a long time, since the standard explanation involving colliding or separating plates simply did not apply. The answer that eventually gained wide acceptance involves something called a hotspot, a fixed plume of unusually hot material rising from deep within the mantle, staying more or less in place, while the plate above it drifts slowly overhead, like a piece of paper being dragged across a candle flame held steady beneath it. As the Pacific Plate has crept northwestward over many millions of years, this stationary plume has burned through it again and again, leaving behind a long trail of volcanic islands and underwater mountains, each one older than the last as you travel away from the current hotspot, which sits beneath the big island of Hawaii today, still actively building new land even as its older neighbors, the islands to the northwest, have gone quiet and slowly begun to erode back into the sea. Iceland offers yet another variation, sitting not on a subduction zone and not quite on an isolated hotspot in the ocean's interior, but almost directly atop the mid-Atlantic ridge, the long seam where the North American and Eurasian plates are gradually pulling apart from one another, spreading at a rate not unlike the growth of a fingernail, allowing magma to well up steadily into the widening gap. It is one of the few places on Earth where this kind of spreading boundary rises above sea level rather than remaining hidden along the ocean floor, which is part of why Iceland has such a visibly active volcanic landscape relative to its modest size, and why some geologists suspect it may also sit above a hotspot layered on top of the ridge, a combination that is still debated rather than fully settled. Then there is the Mediterranean, home to Vesuvius and Etna, shaped by yet another arrangement, a slow and complicated collision between the African and Eurasian plates that has been folding and crumpling the region for tens of millions of years, producing not a clean subduction arc, but a messier zone of fragmented microplates grinding against one another in ways that geologists are still working to fully map. And further inland, cutting through East Africa, a very different kind of feature is slowly taking shape. A rift, a place where the continent itself is gradually pulling apart, thinning the crust and allowing volcanoes like Kilimanjaro and Nyiragongo to form along a boundary that is, in a sense, still being born. So when you picture a globe scattered with volcanoes, it helps to remember that they are not scattered at all. Not really. They trace the seams of the Earth's shifting shell, one story in the collision and sinking of the plates around the Pacific, a second in the fixed, patient plumes that burn through drifting plate from below, and a third in the slow pulling apart of crust that is stretching thin enough to let the interior show through. Understanding which story applies to a given mountain turns out to matter enormously for predicting what it might do next, which is where the story of volcanic monitoring itself begins to take shape. There is another side to this story, though, one that gets told less often, perhaps because destruction makes for a more urgent headline than creation does, but it is worth sitting with for a while, especially at this hour, because it is a story that unfolds so slowly that no single human life is long enough to witness its beginning and its end. Consider Hawaii, the islands you can point to on a map today, the beaches, the green valleys, the little towns tucked into the folds of the mountains. All of that is lava. Not lava in some abstract geological sense, but literally the cooled and weathered remains of eruptions stacked on top of one another, one flow at a time, for hundreds of thousands of years, rising up from the ocean floor until they finally broke the surface and kept going. The Big Island itself is still being built. Kilauea has been adding new land along its southeastern coast for decades now, sending lava down to the shoreline where it meets seawater in a hiss of steam, hardens black and glassy, and becomes, however briefly in geological terms, new ground. People have stood at a safe distance and watched entire acres appear in a single afternoon, a strange and quiet kind of birth, the coastline rewriting itself in real time while the rest of the world goes on unaware. This has happened before in ways that were even more directly observed. In November of 1963, fishermen off the southern coast of Iceland noticed something strange in the water, a smell like rotten eggs, then a plume of dark smoke rising where there had been only open sea. Within days, an island was forming, and scientists arrived to watch a landmass emerge from nothing, layer by layer, explosion by explosion. They named it Surtsey, after Surtur, a fire giant from Icelandic mythology, and it kept growing for about 4 years before the eruptions finally stopped, leaving behind a small island of black rock roughly a square mile in size. What makes Surtsey remarkable is not just that people got to watch a piece of land being born, but what happened afterward. Iceland declared it a nature reserve almost immediately and kept it that way, banning nearly all human visitors, precisely so that scientists could observe, undisturbed, how life finds its way onto a place that begins as nothing but sterile volcanic rock. A few seeds arrived on ocean currents. Birds began landing to rest, and their droppings carried more seeds, along with nutrients the soil badly needed. Moss appeared first, then lichen, then grasses, then eventually, enough soil had built up that small shrubs could take root. Watching Surtsey has been, in a sense, like watching a fast-forwarded version of what happened to every volcanic island that has ever existed, a process that usually takes so long it disappears into the blur of geological time. Because this is really the pattern behind every volcanic island chain on Earth, whether it is the Galapagos, or the Canary Islands, or the countless islands scattered across the South Pacific. Bare rock, at first, inhospitable and sharp underfoot, nothing but stone cooling in salt air. And then, slowly, the arrival of life carried by wind and wave and wing, and slowly again, the transformation of that rock into something that can hold a root, something dark and crumbled, and rich enough to be called soil. This brings us to something volcanoes are, perhaps surprisingly, quite good at, which is making some of the most fertile ground on the entire planet. It seems almost contradictory at first, that the same eruption capable of burying a town in ash could also be quietly laying the foundation for extraordinarily productive farmland. but the chemistry works out in a way that makes a kind of patient sense once you slow down and follow it. Volcanic ash is rich in minerals that plants need to grow, things like potassium, phosphorus, and calcium, locked up inside tiny glassy fragments of rock. On their own, freshly fallen, those minerals are not yet available to a plant's roots. But over years and decades, rain and weather slowly break the ash down, dissolving it, releasing its minerals into the surrounding earth in a form that roots can actually use. The volcanic soils that result, sometimes given the technical name andisols, tend to hold water unusually well, resist compacting, and stay loose and workable in a way that many farmers over the centuries have come to prize, even when they had no idea why the ground beneath their feet behaved so differently from the ground a few valleys over. You can see this today on the slopes of Vesuvius, where vineyards climb the same mountain that buried Pompeii nearly 2,000 years ago. Grapes have been grown there for a very long time, long enough that Roman writers described the wine of the region with real affection, and the tradition never really stopped, even after the eruption of 79, even after later eruptions that came in the centuries following it. Farmers kept returning to those slopes, generation after generation, drawn back by soil that reliably outperformed the flatter land nearby, even though it sat beneath a mountain that everyone knew could erupt again. It is a strange kind of trust, built not on forgetting the danger, but on weighing it against a very tangible benefit, one that could be tasted in the fruit itself. The same pattern shows up on the island of Java in Indonesia, where volcanic soil, replenished again and again by eruptions from mountains like Merapi, supports some of the densest agricultural land in the world. Rice paddies terrace their way up hillsides that sit uncomfortably close, by some measures, to an active vent, and yet those hillsides feed millions of people, in no small part because of what the volcano itself has provided over centuries of eruption and rebuilding. Coffee, grown on volcanic slopes in places like Guatemala, Ethiopia, and Indonesia, is often prized specifically for qualities traced back to that soil, a certain brightness or minerality that farmers and roasters alike have learned to associate with land shaped by fire. There is something worth sitting with in this, a kind of quiet balance that runs through the whole relationship between people and volcanoes. The same force that destroys a home can, given time, enrich the ground that home was built on. The same eruption that buries a field in ash is, in its own unhurried way, setting the stage for a field that will eventually grow more abundantly than it did before. None of this makes the danger any less real, and none of it should be mistaken for some kind of cosmic fairness, because the timescales involved are so mismatched. A single eruption can end a human life in seconds, while the soil it leaves behind might take a generation or more to become truly productive, benefiting people who were not even born when the ash first fell. But it does help explain something that can otherwise seem baffling: why humans have lived on the slopes of dangerous volcanoes for as long as recorded history stretches back, choosing again and again to settle in the shadow of mountains that everyone around them knew could, someday, turn violent. It is not recklessness, exactly, or at least not only that. It is closer to a long-standing bargain, made without much conscious thought, between the risk of a single terrible event and the promise of fertile ground for many quiet, uneventful years in between. And understanding that bargain, understanding how people learn to read the moods of these mountains well enough to make peace with living so close to them, brings us naturally to the question of how anyone manages to keep watch over something so vast and so slow and so occasionally, suddenly, fast. It begins, as so much of geology does, with listening. Not listening in the ordinary sense, not an ear pressed to warm rock, but something more patient and more technical, a network of instruments scattered across a volcano's flanks that do nothing but record, hour after hour, the small tremors and swells and exhalations that most of us would never notice, even if we were standing right on top of them. The people who tend these instruments think of themselves less as predictors of the future and more as careful readers of a language that unfolds too slowly and too quietly for human senses to catch on their own. The oldest and still most fundamental of these tools is the seismometer, a device built to sense the shaking of the ground, whether that shaking comes from a distant earthquake or from something moving underneath a volcano itself. Magma does not rise silently. As it forces its way upward through cracks in solid rock, it fractures the stone around it, and each tiny fracture sends out a small seismic wave, a little shudder that a sensitive instrument can detect, even when it is far too faint for a person standing nearby to feel. A single such tremor means almost nothing on its own. Rock cracks under a volcano fairly often, for all sorts of reasons that have nothing to do with an impending eruption. But when scientists start seeing dozens of these small quakes a day, then hundreds, clustered together and gradually moving upward through the crust, as though something is pushing from below, that pattern begins to tell a story. It is a little like listening to a house settle at night. One creak means nothing, but a steady, rising chorus of creaks, all coming from the same staircase, all growing louder, tells you something is shifting that was not shifting before. There is a particular kind of seismic signal that volcanologists have learned to watch for, especially closely, something called harmonic tremor, a continuous, rhythmic vibration, quite different from the sharp individual jolts of ordinary rock-breaking earthquakes. Harmonic tremor is thought to come from fluid moving through narrow passages underground, magma or volcanic gas, pushing and pulsing its way through cracks in a way that sets up a steady resonance, not unlike the way air moving through a flute produces a sustained note rather than a single tap. When this kind of tremor appears and strengthens, it often means that molten rock is actively on the move, no longer just cracking its way upward but flowing, and that shift from broken, isolated quakes to a smooth, continuous hum can be one of the more reliable signs that an eruption is drawing near. Sound and shaking are only part of what a mountain gives away, though. Volcanoes also swell, almost imperceptibly, as magma accumulates beneath them, and detecting that swelling has become one of the central tools of modern monitoring. Picture a mountain not as something fixed and immovable, but as something closer to a slowly filling balloon, its surface rising by centimeters, sometimes only millimeters, as pressure builds underneath. Instruments called tilt meters, some of them sensitive enough to detect a change in slope smaller than the tilt caused by a person walking past, sit anchored into the ground and register these shifts continuously. Alongside them, GPS receivers, similar in principle to the navigation systems in a car but far more precise, track the exact position of points on the volcano's surface day after day, watching for the kind of gradual spreading or uplift that signals magma pooling in a chamber below. It is patient, unglamorous work, watching numbers creep by fractions of an inch. But that patience is exactly the point. A volcano that is truly stirring rarely does so all at once. It swells first, quietly, for weeks or months, or sometimes years, long before anything visible happens at the surface. Gas tells its own part of the story too, and it is often gas that first hints at magma approaching from very deep within the earth. As molten rock rises toward the surface, the pressure surrounding it drops, and dissolved gases that were held in solution begin to come out, not unlike the way bubbles form in a bottle of soda the moment it is opened. Sulfur dioxide is one of the more useful of these gases to track, because it is relatively rare in the atmosphere from other sources and can be measured from a distance, sometimes even from satellites orbiting far overhead. When the sulfur dioxide pouring out of a volcano's summit or flanks begins to climb sharply, it often means that fresh magma is arriving from deeper in the system, magma that has not yet had the chance to lose its dissolved gas the way older, more stagnant magma has. Scientists standing near a crater with a handheld spectrometer or reading data beamed down from a satellite hundreds of miles above are, in a real sense, smelling the mountain's breath and noticing when it changes. None of these signals mean much in isolation, and this is perhaps the hardest lesson volcano science has had to learn, often at painful cost. A swelling ground with no earthquakes might simply reflect groundwater shifting rather than magma rising. A burst of earthquakes with no ground deformation might be ordinary tectonic activity that has nothing to do with the volcano at all. It is only when several of these threads braid together, rising seismicity, measurable swelling, increasing gas output, that scientists begin to feel confident that something significant is underway. Even then, confidence comes in degrees, expressed not as a yes or no, but as a shifting color on an alert level scale. Green through yellow, through orange into red, each step meant to communicate not certainty but changing probability, an honest acknowledgement that the Earth's plumbing remains, in the end, only partly visible from the surface. This kind of watching has a long and human history behind it. In the early 20th century, a geologist named Thomas Jagger grew troubled by how little warning people had received before deadly eruptions elsewhere in the world, and in 1912 he helped establish an observatory on the rim of Kilauea in Hawaii, one of the first places on Earth where scientists committed themselves to watching a volcano continuously, day after day, rather than studying it only after disaster had already struck. That observatory, and the ones that followed its example around the world, rested on a simple but hard-won idea that a volcano's dangerous moments are usually preceded by quieter ones, and that if someone is patient enough to keep listening through all the quiet years, the mountain will eventually offer some kind of warning before it turns violent. That patience paid off dramatically in June of 1991, when Mount Pinatubo in the Philippines, a volcano that had been dormant for roughly 500 years, began showing the unmistakable signs scientists had learned to recognize: swarms of small earthquakes, swelling ground, surging sulfur dioxide. Teams from the Philippine Institute of Volcanology and Seismology, working alongside American colleagues from the United States Geological Survey, watched these signals intensify over the course of weeks and made the difficult call to recommend evacuation before the largest eruption arrived. Tens of thousands of people left the surrounding slopes in the days before the mountain's climactic explosion, one of the largest eruptions anywhere on Earth in the 20th century. Estimates suggest that warning and evacuation saved thousands of lives that would otherwise have been lost, a rare case in which the slow, careful accumulation of scientific listening translated directly and unmistakably into people walking away from danger while there was still time to walk. Not every volcano offers such clear warnings, and not every warning is heeded quickly enough, which is part of why this work continues without pause, sensors humming quietly through the night, in places most of us will never visit, gathering the small, patient evidence of mountains getting ready to speak. Long before anyone measured sulfur dioxide or listened for the tremor of magma moving underground, people were already listening to volcanoes in a different way, through story. It is worth resting here for a while, away from instruments and evacuation routes, and thinking about what these mountains have meant to the people who lived beside them, sometimes for their whole lives, sometimes for generations stretching back further than anyone could count. In Hawaii, long before Thomas Jagger built his observatory on the rim of Kilauea, the volcano already had a name and a presence far older than any seismograph. Pele, the deity associated with fire and volcanoes in Hawaiian tradition, was understood not as a distant force, but as someone who lived within the mountain, whose moods could be read in the glow of the crater at night or the sudden opening of a new fissure. Offerings were left at the crater's edge, chants were composed in her honor, and her long journey through the islands, moving from one volcanic center to another as older craters cooled and newer ones opened, mirrored something that geologists would only later confirm through careful mapping, that the Hawaiian Islands themselves form a chain marking the slow northwestward drift of the Pacific Plate over a fixed hotspot of rising heat. The story and the science describe the same journey, one in the language of a goddess walking from island to island, the other in the language of plate motion and magma supply, and there is something quietly moving in the way both arrived, independently, at a description of movement across the same stretch of ocean. Across the world in the Mediterranean, the volcano of Etna on the eastern coast of Sicily carried its own layers of meaning for the many peoples who settled around it. The ancient Greeks who colonized Sicily imagined the giant Typhon, or, in some versions, the monster Enceladus, pinned beneath the mountain by the gods, his struggling breath rising up as smoke and his shifting weight felt as tremors in the ground. Later, Roman writers folded Etna into the workshop of Vulcan, the god of fire and metalwork, whose forge supposedly burned beneath the mountain, hammering out weapons for other gods in the deep dark below the slopes, where farmers tended vineyards, planted in soil, made unusually rich by centuries of settled ash. It is a small, telling detail that some of the most fertile farmland in Sicily sits directly on the slopes of an active volcano, a fact that shaped where people chose to live for thousands of years, weighing the quiet, patient gift of fertile soil against the occasional and sometimes terrible cost of eruption. That same tension between a volcano's gifts and its dangers appears again and again wherever people have settled near these mountains, and it may be one of the oldest and most universal relationships in human history. In Japan, Mount Fuji has been revered for over 1,000 years, climbed as a pilgrimage by believers in Shinto and Buddhist traditions alike, its nearly symmetrical cone appearing in paintings and poems as a symbol of stability and permanence, even though the mountain last erupted in the early 18th century, and geologists consider it very much capable of erupting again. There is something almost tender in the way a civilization can build centuries of reverence and artistic tradition around a mountain whose deep nature is neither stable nor permanent, but rather a paused conversation between the Earth's interior and its surface, waiting to resume on a timescale too slow for any single human lifetime to witness more than a fragment of it. In Indonesia, where more active volcanoes cluster together than almost anywhere else on Earth, Javanese tradition speaks of Kelud and other mountains as the dwelling places of powerful spirits who require respect and periodic offerings, rituals that continue in some communities even today, carried out by farmers who have watched their grandparents perform the same ceremonies and who understand, in their own way, that they are negotiating a relationship with something vast and only partly predictable. Nearby, the eruption of Krakatoa in 1883 produced sounds so loud they were heard clearly more than 3,000 kilometers away, understood at the time by people along the shores of the Indian Ocean as something closer to distant cannon fire than to any natural event they could easily name, a reminder that a single volcano can reach into the imagination and the record books of places that never saw its ash fall or felt its ground shake. The Icelandic sagas, composed and passed down starting around the 12th century, describe a landscape shaped constantly by fire beneath the ice, and Icelandic settlers understood early on that their island sat somewhere unusually active, though they lacked the vocabulary of plate boundaries and mid-ocean ridges that would only be developed many centuries later. They knew instead through direct experience, through the black sand that covered their fields after certain winters, through the strange red glow sometimes visible on the horizon at night, through stories told about mountains that had once opened up and poured fire across pasture land that had taken generations to make usable. When the volcano Laki erupted in 1783 and 1784, releasing enormous quantities of gas that poisoned crops and livestock across the island, it caused a famine that killed roughly a fifth of Iceland's population, a catastrophe severe enough that it likely also affected weather patterns across parts of Europe that same year, contributing, some historians believe, to unusually harsh winters and crop failures far from Iceland's shores. It is a sobering thought to sit with quietly here in the dark, that a single eruption on a remote island can ripple outward into harvests and lives thousands of miles away, connecting strangers across a continent through nothing more than shared air and shared sky. Even in places without active volcanoes today, the memory of ancient eruptions has sometimes lingered in cultural memory far longer than seems reasonable at first glance, preserved not in written records, but in oral tradition, passed carefully from one generation to the next. Aboriginal Australian stories describing volcanic activity in places like Victoria's newer volcanics province appear to describe eruptions that occurred many thousands of years ago, a span of time that, if the connection holds, would represent one of the longest continuously maintained oral traditions known anywhere in the world, carrying forward the memory of fire from the ground long after the mountains themselves had gone quiet and the landscape had settled into what looks. What runs through all of these stories, whether they come from Hawaii or Sicily or Iceland or Java, is a recognizable human effort to make sense of something enormous and only partly visible, using whatever language and imagery a culture had available at the time. A goddess walking between islands, a giant pinned beneath a mountain, a spirit requiring offerings, a forge tended by a god of fire. These are not mistakes to be corrected by later science, so much as they are earlier attempts at the same fundamental task that seismographs and gas sensors perform today, the task of listening carefully to something vast and mostly hidden, and trying, with whatever tools are at hand, to understand what it might do next. And perhaps that is worth sitting with for a moment before drifting further, the quiet realization that long before anyone measured a tremor or mapped a plate boundary, people were already paying attention, already noticing the soil, the smoke, the sudden silence before a change, weaving what they observed into stories meant to be remembered and passed down carefully, the way we might now pass down a warning, or a map, or a number on a screen showing how much the ground has moved since yesterday. So let the stories rest now, the way the mountains themselves so often do, and let the mind settle back down toward something simpler than myth, something closer to just watching, the way you might watch a candle burn low in a dark room, no longer needing to understand the flame, only content to notice that it is there and that it is quiet. Picture, if it helps, a single mountain somewhere, it hardly matters which one, standing the way mountains stand, which is to say, without any apparent effort at all. Snow, perhaps, settled along its upper slopes, or cloud, resting against its shoulder, the way a blanket settles against a sleeping shoulder, shifting slightly with the wind, but otherwise unmoving. From a distance, at this hour, it looks like exactly what it appears to be, a fixed and permanent shape against the sky, the kind of landmark a person might use their whole life to know which direction is home. And in a certain sense, that stillness is not a lie. Most mountains, most of the time, are exactly as quiet as they look. The magma, if there is any waiting beneath, is patient in a way that has no real equivalent in a human life. Patient across years that blur into decades, that blur into centuries, cooling by degrees, so small they would never register on skin, crystallizing slowly in the dark the way frost gathers on a window overnight, one imperceptible layer added upon another until, decades later, someone notices the pattern has changed. It can be strange to hold both of these truths at once, that a volcano is a violent thing, and also, for the overwhelming majority of its existence, an almost perfectly still one. The eruptions that fill the history books and the memory of villages are brief interruptions in something otherwise unhurried, flashes of intensity set against years, sometimes centuries, of quiet accumulation. A mountain like the ones we've walked through together over these hours does not live at the pace of a human story, with its rising action and its climax and its resolution. It lives instead at the pace of sediment settling in a lake, at the pace of stalactites lengthening drop by drop, at the pace of a coastline reshaped so slowly that no single person could ever witness the change, only infer it from what the rocks left behind. To the mountain, 100 years of silence is not a long wait. It is barely a pause, and so when we speak of a volcano being dormant, or being watched, or being due for something, we are borrowing timescales that do not naturally belong to us, trying to fit the patience of stone into the patience of a human life, which is, understandably, a much shorter and much more anxious kind of patience. If you widened the view far enough, out past any one mountain and any one range, you would begin to see the whole outer shell of the planet as something closer to a set of slow-moving rafts, vast plates of rock drifting across a softer layer beneath them, at a pace not much faster than a fingernail growing, a few centimeters most years, so gradual that nothing about it ever feels like motion from where we stand. And yet it is motion, real and continuous, carrying continents apart in some places and pressing them back together in others, tearing the ocean floor open along mid-ocean ridges where fresh rock rises up warm and dark and takes its place as new seafloor, and, thousands of kilometers away, feeding that same old rock back down into trenches where one plate slides beneath another and begins its long, slow return into the planet's interior. Volcanoes tend to gather along these boundaries, whether spreading or colliding, because that is where the crust is thinnest, or most broken, or most easily persuaded to let something rise through it. A chain of islands, a line of coastal peaks, a ridge running unseen along an ocean floor, all of them tracing, in their own patient way, the seams where the Earth's outer shell is either being made new or being folded back down into the furnace it came from. It is, in its slow and wordless way, a kind of recycling, the same atoms of carbon and iron and silicon cycling from mantle to crust to ocean floor to trench and back to mantle again, a circulation with no beginning that anyone could point to, and, so far as anyone can tell, no ending in sight either, at least not on any calendar we would recognize. There is something almost restful in admitting that mismatch of scale honestly, rather than fighting against it. We are creatures who notice change on the scale of a season, a year, perhaps a single lifetime, if we are fortunate enough to watch something slow unfold across our own decades. The Earth does not share that rhythm, and it was never going to. It has been building and unbuilding itself since long before anything with eyes existed to watch it happen, folding oceans into mountains, and mountains back into sediment, opening rifts and closing them again, breathing out gas in great restless plumes, and then falling silent for spans of time that make even the oldest human civilizations look like something that happened only a moment ago. If the whole span of the planet's history were compressed into a single ordinary day, human beings of any kind would appear only in its last few seconds, and everything we have ever built, every pyramid and cathedral and city grid, every story we have told about fire gods and sleeping giants, would fit into a sliver of time too thin to notice without looking very closely. Against that backdrop, our worry about any particular mountain, however reasonable and however well earned by the science, is a small and human-sized thing, precious, precisely because it is ours, but not something the mountain itself is waiting to hear. And yet within that vast and largely silent history, people have always found ways to live alongside these restless places, not merely enduring them, but, in many cases, building lives that depend on them. The same slopes that occasionally threaten a village are often the reason that village exists there at all, because volcanic soil, once it has had time to weather and settle, tends to be extraordinarily fertile, rich in minerals that plain sedimentary ground rarely offers, which is why the slopes of Vesuvius still support vineyards, why farmers in Java and the Philippines and Central America return again and again to plant in the ash-darkened earth, even after it has proven, more than once, exactly what it is capable of doing. Geothermal energy, drawn from the same deep heat that drives an eruption, now warms homes and generates electricity in Iceland, in parts of Kenya, in New Zealand and Japan and the American West, a way of borrowing gently from the same furnace that, elsewhere and under different pressures, produces something far less gentle. Hot springs draw travelers to soak in mineral-rich water heated by rock that never sees daylight. Obsidian, formed from lava cooled too quickly to crystallize, was shaped into some of the sharpest tools human hands have ever made. Edges thinner than glass, prized by toolmakers long before anyone understood where the material had come from. None of this erases the danger. It simply means that danger and usefulness have always traveled together in these places, two faces of the same deep heat, and that the people who live closest to volcanoes have, across thousands of years, learned to hold both truths at once, without needing to resolve them into a single simple feeling. None of this means the danger isn't real, or that watching stops mattering, only that the watching can be done gently, the way a parent checks on a sleeping child without needing to wake them, a soft hand against a door left slightly open, not fear exactly, just attentiveness held loosely. The scientists we've mentioned across this long, unwinding explanation, the ones reading tilt from a hillside or gas from a crater, or the pitch of a tremor recorded in the dark, are doing something not so different from that quiet check at a bedroom door. Today that watching happens through instruments spread quietly across a mountain's flanks, seismometers listening for the faint underground rumble of magma forcing its way through rock, tilt meters and GPS stations sensitive enough to notice a slope swelling by only a few millimeters as pressure builds beneath it. Gas sensors sampling the crater's breath for the particular sulfur signature that often rises before an eruption, and, high above all of it, satellites capable of measuring the ground's slow deformation from orbit, comparing one image to another taken weeks apart, and finding, in the tiny differences between them, the first quiet evidence that something below has begun to shift. None of these tools can say with certainty what a mountain will do or exactly when, because the underlying system remains, even now, only partly understood. But together they allow the people who study volcanoes to notice change earlier than they once could, to move a warning ahead of a crisis instead of behind it. They are not trying to stop the mountain from doing what mountains eventually do. They are only trying to notice a little sooner than they otherwise would. so that the people living nearby can move a little sooner too, can gather what matters and step back and let the ground do, in its own slow time, whatever it was always going to do, regardless of anyone's permission. And maybe that's the last thing worth carrying forward from everything we've walked through tonight, past subduction zones and hot spots, past ash clouds and lava tubes, past gods with hammers and goddesses walking barefoot between islands, past every confusing word finally set down gently in plain language. The earth is not trying to frighten anyone. It is simply doing what it has always done, moving heat from its deep interior toward its surface in whatever way the rock and the pressure and the chemistry happen to allow, sometimes so slowly that whole forests grow and die across a single dormant century, sometimes quickly enough to reshape a coastline in a single afternoon. Both of those speeds belong to the same process. Both are, in their own way, the planet breathing. The same slow exhale that built the Hawaiian Islands one patient layer at a time, and the same restless churn that once, hundreds of millions of years ago, joined every continent into a single vast landmass before pulling it apart again into the shapes we now take for granted on a map. Shapes that are still quietly drifting, still trading fractions of an inch a year, still becoming something slightly different than they are tonight. If you have made it this far, past all of it, past the plates sliding beneath each other in the dark, past the difference between magma and lava, past the strange particular danger of a volcano that seems gentle right up until the moment it isn't, past the long, patient wait of Yellowstone and the sudden furious wake of Vesuvius, then perhaps you can let all of it settle now, the way ash eventually settles, the way a tremor eventually fades from the seismograph back into a flat and steady line. There is nothing more to solve tonight. The mountain, wherever it is not going anywhere in the next few hours. It has been standing for longer than anyone currently alive has been alive, and it will very likely go on standing long after tonight has become nothing but a page in a calendar no one thinks about anymore. Whatever it is doing, deep beneath its calm exterior, it is doing on its own schedule, unconcerned with hours, unconcerned with the hour, unconcerned with whether anyone is awake to wonder about it. So let your own breathing slow instead, the way the tremor line slows, the way the smoke over a quiet crater eventually thins to nothing against the sky. Let the questions rest where they are, unfinished maybe, but held gently instead of urgently, the way a river holds a stone rather than fighting it, wearing it smooth over centuries instead of trying to move it all at once. Somewhere out there tonight, a mountain is standing exactly as still as it has stood for years, its slow interior chemistry unfolding at a pace too vast for worry, too vast even for careful attention, moving only the way deep, patient things move, a little at a time, in the dark, without any hurry at all. You can rest the same way. Nothing tonight requires urgency. Nothing tonight requires an answer before morning. Let the mountain keep its watch, quiet and immense and unbothered by the hour, and let yourself finally, gently, let go. Rest well.